Thank you. Good morning. I do realize that I'm competing with a very strong slot with Alex over there. I'll be talking about my PhD research in multimodal emotion recognition. So maybe just to explain my affiliation, I'm doing my PhD with Cambridge University, but I'm also based at the University of Pretoria under Professor Engelbrecht. So this is some work that I did within those two groups. And so what I'll do is that I'll give an overview of what emotion recognition is about, where does it come from, and why do we care as computer scientists. And also then look into the procedure, or rather the process of recognizing emotion. So extracting features, feature reduction, and also how do we model the emotions, and looking at some variants of recurrent neural networks. And then I'll touch up also on the model that I've been working on called the continuous conditional recurrent neural field. So in order to start, I think it's just fitting first to show you why we are interested in this field, or why I'm in this field. So imagine, at one point in our lives, we must have felt frustrated with our computers. Now imagine if our computers could detect the frustration before we get to the stage and then respond to our frustration and try and calm us down. Then we would, we would have a better relationship with our computers. So that's the whole aim of affective computing. So let me just provide an overview into the historical context of it. So it's a relatively new field, started in the 90s, and the term affective computing was coined by Professor Rosalind Picard from MIT, and in her 1995 paper, where she defined affective computing as computing that relates to, arises from, and deliberately influences emotion. And in her talk, she said, or rather in her paper, she mentioned that a computer should be able to recognize a person's emotional state, adapt its behavior to them, and give an appropriate response to the detected emotions. So the field of affective computing basically encompasses all these elements. So trying to recognize the emotion, and then once we recognize the emotion, how do we then have intervention strategies to adapt to the user's emotion, and then how do we respond also to that? And this
Ntombi, I'm going to be incredibly rude.
Okay.
Sorry for interrupting, but for the sake of the recordings, all of these sessions are being recorded. I'm just going to ask you to quickly pop the microphone onto the person. Otherwise, the whole world can't hear what you're saying. So I'm just going to go ahead there, and go ahead and stop.
Okay, thank you. No problem. So these are the basic elements of affective computing, and there's quite a lot involved. And as you can see, it's an interdisciplinary research combining psychology, computer science, and a number of fields. And the premise of it is based on a study by Reeves and Naz in 1996, where they have a hypothesis that computers are close enough to humans that they encourage social responses and therefore will get human treatment. So what they did is that they created a study where they studied how people relate to computers. And their findings were that people treat computers as real people, and the interactions are fundamentally social and natural. So you would treat a computer as if it were another person. The way you speak to it, you would have empathy, not empathy, but you would speak to it with emotion. And I just have a video to illustrate that concept. So hopefully the audio won't be too bad. But so you could see the discussion. It's as if you're talking to somebody like, okay, it's okay. There's no monotonous discussion or So there's quite a lot of emotion in it and the way that the child relates to computers. So, and they found that people in general, that's how we relate to computers in such circumstances. So the important thing is, or rather the key thing here is that emotions, we find that emotions are central to human experience, behavior, and are inherent in all forms of communication. And in fact, Mahaban came up with this model where he said that the predominant form of communication is actually nonverbal. So when you talk to somebody, the message is actually carried or conveyed within your nonverbal language or nonverbal behavior. And so 55% of, so the message is conveyed, rather, the body language accounts for 55% of the message, and the voice and tone account for 38%, and the spoken words actually just account for about 7% of those words. So there's quite we read into a lot of nonverbal behavior or your body language when we speak to people. And that's why it's then important then to, when we create such systems, that we need to analyze the nonverbal behaviors, and we use that as the primary vehicle for emotion expression. And also when we design such systems, we base then our analysis on the nonverbal behaviors. So we analyze the facial expressions, we analyze the body postures, and that's the foundation of affective computing. So for computer scientists, what we're interested in is how do we then represent emotion, because it sometimes feels abstract. And the psychologists have a huge debate on what emotion is and the theories, what triggers emotion or what happens before that. So as a computer scientist, I'm not going to go into those theories. We're not really interested in that. But we just we just have a cursory look at what they're saying, and then look at how we can then model or create models based on what they've come up with. So initially in the field, we've concentrated on discrete emotions. And this is a theory that was initially sparked by Darwin's evolutionary theory, where he went around and saw that there are some expressions that are pancultural, or that are the same regardless of where you come from. And so we call them universal expressions. And those are the 6 expressions: the happy, sad, fear, anger, surprise, and disgust. And so initially, most of the research in affective computing worked on recognizing these 6 emotions. And while it was exciting and performance improved, the truth about these emotions that you don't really experience this in your normal working environment, right? We tend to have complex emotions, subtle emotions. For example, we want to detect frustration or boredom, especially if you're going to be working on a system that works with kids or an intelligent tutoring system. So you want to be able to detect such emotions. So the computer scientists looked for ways then of going beyond the scopes, and then there are different theories then behind it. So another model then that came up is the dimensional emotion model, where we analyze emotions, or where we view emotion along 2-dimensional, or rather along 2 dimensions: the valence dimension, where it looks at positive and negative feelings, and also the arousal, where it looks at the intensity of emotion. So excitement, agitation, and the low arousal could be depressed, sad. So those are the type of emotions that are contained within. And there's a theory of Russell that came up that said that actually you can represent quite a lot of emotions within these 2 dimensions, and they all fall within the spectrum. And within this dimensional emotion model, you can then you can create models that either look at categorical emotions, discrete emotions, or we look at continuous emotions. So looking at emotions, so providing a numeric value to an emotion. For example, when you're looking at arousal, you could look at in the spectrum between -1 and 1, how aroused is this person. So my work is looking at continuous dimensional emotions. So I base my models on the dimensional emotion theory, focusing on continuous emotions. So I've mentioned a few about the modalities that we use when detecting motion. So as humans, when we talk to people, we analyze a number of things. There are a lot of processing happens in our brains. For example, we look at facial expression, we look at the body posture, we look at the tone, So the vocal quality, and we also look at like head gestures. So it's then, so initially, most of the work was in facial expressions, and then we later decided, hey, maybe let's try and emulate humans and then incorporate all these other modalities. And that's how we came up with, or the research of multimodal emotion recognition started up. So we're looking at how then do we fuse these different modalities. Firstly, how do we extract features from the different modalities, and then how do we then fuse them to be able to better our emotion recognition rates. And this is just an overview of the emotion recognition system. So you first start off with your features that you will extract. So you'd extract some features from your images, from audio, and from your biosignals, and then pass those features into some, pre-process those features either by reducing the dimensionality, and I'll touch upon that, and then also then modeling the emotions, and then looking into fusion strategies, and then that gives out your predicted emotion. So in terms of applications, there are many applications. So I'll just list some of them. One of them is, and this is very big in Japan, the elderly care and companion. Because of the population dynamics, they've invested a lot of money in robotics, and so that because what happens is they have a large elderly population and they tend to become lonely, so they've then looked into what devices they can create or what robotic systems they can create to then keep the elderly people, to keep them accompanied. And in that case, emotion plays a very important role, because you can't just be spending time with the robotic system and there's no communication, there's no natural communication between the two. So there's a lot of research within that field. Then education, as I've mentioned. So when we have intelligent tutoring systems, we want to be able to detect when a child is frustrated or when they're having problems with this, but also when they're doing well, so that we know then maybe we should reduce the amount of times we help them with these questions. And then also we look at remote therapy, and that's in here we look at avatars and speech synthesis, so also synthesizing emotion in speech. And also another big area is autism therapy. That's because the children with autism, with autistic children, tend to have difficulties reading facial expressions, and then they found that using robotic devices or using robots to teach them facial expressions, because they are consistent in how they express those facial expressions, then they're able to learn or have a better recognition rate after dealing with after dealing with these devices. And then also we're moving towards games, emotion aware, so entertainment industry. And another example that MIT has actually capitalized on is the advert viewer reaction. So what they do is, when you watch for focus groups, when the companies want to figure out, or when they want to find out if their ad reaches the punchline or is effective, what they do is that they make people watch this video and analyze their facial expressions, and then the system will tell them whether their marketing strategy meets their whether the marketing strategy is in point. And then also we have mood music players. So these are just the applications that we use emotion recognition in. And the next step that I want to deal with is, how do we then extract emotion, or what type of emotions are then relevant for emotion recognition systems. And to start off, I want to just show you this video.
There are 6.5 billion people in the world, but we all look the same when we lie. Dilated pupils, oblique eyebrows, an upturned lip, the smallest line on your face, the slightest body movement. It all tells a story. It may be human nature to lie, but the truth is written all over your face. Lie to me. News this January on Fox.
So this was a promo for a series called Lie to Me. And what I like is it actually captures what facial expression analysis is about. So we're looking at what happens in your face when you convey different expressions. And those concepts, or rather those muscle movements are what we use then as features for our emotion recognition system. So for visual features, we have broadly three categories: your geometric features, appearance features, and motion features. And I'll just quickly highlight the three. So the geometric features, those are based on the facial action coding system that was created by Paul Ekman and Wallace Friesen. And what they do is they analyze the facial movements or muscle movements as you elicit or as you convey different expressions in your face. And then they looked at the combination then of movements to be able to map those to an emotion. And they came up with what we call action units. So looking at the categories of facial movements like an eyebrow raise, an eye furrow. So in the early research, so we looked at and studied all these facial movements and tried to then detect them by looking at the distances. So what will happen is as a person interfaces with the computer, there will be a video camera, and as they talk or as they elicit the emotion expressions, we will then have a facial point tracker, which will then track the different points in the face, and then the deformation of these muscles will then be captured through the distances, and would use these distances then as features, and maybe some what do you call the angles between these points, then use those as features. And those are called the geometric features. So they describe the visible facial muscle movements, and the fact system also includes head movements. Then we have appearance features, and those represent texture of the face, so as a result of an emotion expression. So you're looking at ridges, so at furrows and wrinkles, and we're looking at where they occur, the extent at which they occur, and there are a number of methods then that can be used. So the local binary patterns, although some of these methods have actually been extended further to include different time. For example, there's the three orthogonal planes of LBPs, and then another one is the local phase quantization, and then histogram of oriented gradients, and basically creating histograms of the gradients within blocks of this image. And we use then those as features as appearance features for emotion recognition system. And then the other set is then the emotion features, where we track facial points across frames to create a motion map. And an example of that is the histograms of optical flows, and basically hoping that as the face forms deforms as the emotion evolves, then you can kind of like get a histogram view of what happens, and then use that for mapping such movements to an emotion. We then move on to audio features. And to be able to understand audio features, although our previous speaker has spoken a lot about that, so that we use a lot of the knowledge from speech recognition, although we look at different elements in the audio features. But basically the way that speech is produced is that you first have an energy source, so through the breathing in, which then forces in some air throughout the lungs, and then your vocal folds vibrate at a certain frequency, so we call that the fundamental frequency, and which is then the pitch, and then also then your nasal area and the mouth area then shape those vibrations into sounds, and then out comes the words. So when we look at audio features, we're interested in finding out then what parts of this system, or what parts of the system then can we then borrow from, or can we extract to be able to get our audio features. So there had been a lot of studies, people trying different things, looking at different features, extracting maybe stuff like pitch and glottal features and quite a lot of stuff. Then a few years back, then a group of audio scientists sat together and decided, hey, maybe let's create a minimalistic acoustic parameter set where everybody will kind of like use that as the base so that we're able to compare our models and be able to actually see which models perform better. Because if we're all using different features, then we can't really have a neutral, we can't really find out reliably which model performs better. And since then, this has been kind of like the go-to feature set that we use. And this feature set is then divided, so it's available online, the Geneva Millistic, and it's offered also as a config file for feature extraction tools that deal with audio. And they divide they group their features into 5 categories. So first, the frequency-related features. So they look at the pitch, and also there's some statistical functions that we calculate the mean, the variance, and all related features basically features that relate to the frequency. And those features actually help us to differentiate between high arousal and depressed states. And then the other feature set is the energy amplitude features, which look at the perceived loudness, and then they can help us differentiate between low arousal feelings such as sadness versus your high arousal feelings such as anger. And we also have spectral features, so the shape of the power spectrum, and that represents valence information. Remember, valence is positive versus negative emotions. And then also we look at voice quality features, like how tense your voice is, the breathiness of your voice. And the last one is your temporal features. So we're looking at utterance duration, the amount of silences in the words, how long it takes to utter, okay, I've mentioned that, how long it takes to utter words, and because that can tell you then the information about the state of the person is. So it varies with emotion. And then we also have bias signals, and quite a lot of them. I've only worked with these 2, which is the ECG, where you're looking at electrical activity over time, electrical activity of the heart over time. And it's normal when a person is excited, you might expect a fast heartbeat, or when they're nervous, a fast heartbeat, versus when they're depressed, or when something happens, or also a neutral state where you have then your normal heartbeat. And then also the EDA features, where we'll study the electrical activity of the skin resulting from sweat gland activity. So normally when you're nervous, your hands tend to sweat, so we try and look at the electrical properties of those, that activity then within your sweat glands. So the thing about these features that we extract is that these feature extraction methods tend to yield high number of features. For example, the garble features, you end up having 3,200 features. And when you're looking at temporal local binary patterns, you can have 1,000 plus features. And that quickly leads to what we call curse of dimensionality, when you have too many features, little data, and so your model basically cannot fully learn the mappings between the features and your labels. So what we do then is we apply some dimension reduction approaches, and there are 2 types: feature selection, where you select some features, so you create a reduced feature set based on some features, and there are a lot of strategies that you can use for reducing such feature sets. And then feature extraction, where you create new type of features, looking at correlations between the features. A very well-known one is the principal component analysis, the PCA model. And so I've also looked into this. That's part of my PhD, where so Van der Marten created a taxonomy of dimensionality reduction methods, but specifically these relate to the feature extraction methods. And so this just shows an example of this, quite a lot of them. But what we found is that a lot of them actually can be represented using one formulation. And so these are spectral methods, and I'll explain that through the next slides. So the spectral dimension reduction methods have a similar formula in that the first thing you do is that you construct a graph to encode the geometrical information in the data. So you're looking at how points relate to each other, so using some distance measure or histogram measures also, some distance measures between the features. And You then transform that into a kernel by applying some transformation, for example, a Gaussian kernel or some nonlinear transformation, and that also yields Laplacian matrices. And what these the differences between then the methods is that what they preserve. So what properties do they preserve in their strategy to reduce the dimensionality? So in some cases, in the case of PCA, it tries to preserve the covariance of the data, so that it's global geometry. And then you have other methods such as other methods that basically looking like what's this, Laplacian eigenmix that look at local neighborhoods and tangent spaces. So that's the key difference. But another difference that you can also then divide these dimension reduction methods into two approaches. So your linear approaches called projective mappings and your nonlinear approaches called implicit mappings. And with projective mappings is that you try to learn a mapping vector that relates the input data to some low rank representation. So that's how PCA works. And then implicit mappings, basically the embedding is learned within the strategy itself or the model itself. So I mentioned that these models, or rather these approaches, can then be represented by one formula. And this is the formula. So all of them can be solved by generalized eigenvalue decomposition. But the key thing is that the Y represents your low rank representation, so the reduced dimension set that you're looking for, and then the A is the kernel function or your distance matrix that's modified, and you try to, and it differs based on the method that you're dealing with, and you can apply then a Laplacian. No, rather, you can apply some kernel function over this function over the distance matrix, and it will then yield some nonlinear it will perform some nonlinear transformation that helps to then separate the data or to cluster the data to be able to end up with reduced dimensionality. And so the aim of this then is to search for the embedding, so minimize the cost of this while preserving some property. So as I mentioned, you can actually represent quite a lot of these methods using this function. And the challenge with this is that all those methods are actually very computationally expensive. They take about n cubed, where n is the number of samples or number of images in your data set to run, and it takes n squared storage. So if you're working with 10-second videos, that doesn't matter. But in the type of data that I'm working with, we work with 5-minute videos, and that can end up being about 65,000 frames. So now try creating a 65 by 65,000 frame in MATLAB crash system quickly. So then we had to look into how do you then conduct dimension reduction while having such large-scale data. And one of the methods that we looked into is the Nystrom method. So approximate the kernel. And what we do is that we select some representative samples from our kernel matrix and then use that, the subset of, so you can divide it as follows, and then you use this W function and compute then your eigenvalue decomposition on this W function, or in this W matrix, and then extrapolate to, let's quickly see. So you compute the eigen decomposition based on this W instead of this huge A kernel, and then you extrapolate. So I didn't have the formulation here, and extrapolate to the other points, and that's how you then end up reducing the dimension. It turns out that it works very well for quite you can end up using 10, or you can end up training on 10% of the data or less, and it will. When we studied the, what do you call this? When we studied the, when we studied the preservation criteria of of the methods in relation to the methods, in relation to the reduced data set, it turned out to, it still preserves it very well. And then, so let me quickly run to recurrent neural networks. So they've talked a lot about them today. So I just want to quickly get my time. Okay, so I'm good. Okay, that's cool then. So as I mentioned, that we deal with complex emotions, and they require sequential models because you need to capture the temporal evolution of the emotion expression. So if I were to ask you, what emotions are represented in these images? Just at the top of your head. Are they the same emotion or? Sorry? Regret? Are they actually, maybe let me ask, maybe are they the same emotions or different emotions? Somewhat different, right? So it's very difficult to analyze this just based on still images, and that's why we have sequential models. So it turns out that there's a sad, anger, and disgust. So it could be just the actor playing, or maybe we just need a lot of more context to be able to correctly recognize the emotion. And so we use recurrent neural networks because they represent context to the recurrent connections, and they also discover temporal correlations between events. So we call them, initially used to call them deep networks because they're deep in time. And I'll just run through this because they've already laid the foundation. So you just have recurrent corrections between the hidden layers over time. And the only difference then when you're looking at the feed-forward notation based with respect to the recurrent neural network is that you have these recurrent weights, WHH, and the context from the previous time step that's incorporated in your equation. But then, as many of you know, or those who have worked in recurrent neural networks, is that they struggle with vanishing gradients. So as you have very long time sequences, so and just when training the recurrent neural network, so your error kind of like vanishes over time, and then you're unable to capture, you're only able to capture recent information or recent context, but you tend to forget anything from the past. So then came the savior, long short-term memory. And what they did is that they introduced a constant error flow to ensure that the derivative between the hidden layers then does not attenuate, or it basically becomes constant, the error. And just a high-level overview of what that looks like is the different inputs. So a typical neuron is that you have a summation, and then you apply some nonlinear activation function, and then you get your hidden representation. And with the LSTM, you introduce 3 gates, then they're able to regulate the flow of information, decide when to update information or what to forget and when to forget it. And just a summary of the 3 gates. The input gate determines what new information was stored in the cell state. The forget gate, how much previous state to let through or to forget. And the output gate decides what part of the cell state do we then release into the rest of the external network. So either to the other hidden layers, if you have a deep neural network or a deep network architecture, or basically leading to the output node. And they've also mentioned a number of variants, the gated recurrent unit, which uses 2 gates instead of 3, and the single gated unit, which uses 1 gate. And so my work has been on the development of, rather the combination of 2 models. So I looked at is there any, so I was interested in figuring out whether we can leverage the discriminative nature of conditional random fields and then combine that with gated recurrent units to be able to model the emotion sequence. And just an example of what happens in terms of the problem that I'm working on is we try to look at what's the probability then of arousal being 0.6, but because we tend to work with sequences. So what's the probability of arousal being 0.6, then followed by 0.5 and all that, given these features? So fast heartbeat, loud voice, and all that. So that's what the model is trying to capture here. And then the model then, based on that, we try to predict the best sequence of labels for its observed input by searching through all the sequences and return the sequence with the highest probability. And so just a touch up on the conditional random filter, which is basically the foundation of this model. It's that it's very similar to your hidden Markov model, but it just relaxes the input independence assumptions of it. And then instead of modeling the joint probability, it models the conditional probability, which makes it very easy, or easier rather, to model. And then a great thing about it is that we're able to get confidence scores. So we are able to then say, I'm detecting arousal to be this value with so much confidence. And we get that information from the variance of the model. So I'll explain that in the next slide. So the model is based on the principle of maximum entropy. So in short, it says, model all that is known, assume nothing about the unknown. So what we do is that we go through the data and then create a distribution of the labels based on the input. So we try to map the empirical distribution. So the model tries to map the empirical distribution of the data. And then for all those events that we don't know about, we assume maximum entropy. So in that case, we have a uniform distribution for that, because that's when the entropy is at the highest value. So that's the foundation of that model. And it turns out that this actually yields the Gibbs distribution. It's based on the Gibbs distribution. And so there are just key things. Firstly, so we're trying to recognize a sequence of labels based on some input features. And what we do is that we model the input features with regards to target labels, with respect to the target labels. And here, so we look at the association between your output labels and the input with some function applied. And then we also look at the relation between adjacent labels. So this is what this term does. And what I've done is that I've then used a aggregated recurrent unit to then model the prediction of, or the mapping of xt to the yt. And if we assume that y sample from a Gaussian distribution, and I have analyzed my data and it does conform to that, so we can convert this to a Gaussian distribution. And if you look at my papers, there is a mathematical proof, or it does actually translate to this if you work it out. And the nice thing about this is that it makes it so much easier to compute and so much easier to train. And the key things that we can now represent this model using covariance matrix and your mean. And this I've mentioned a bit earlier on, that this, no, I didn't even mention, but it's the Laplacian matrix. So it looks at the relations between the data points. So it's very similar to what we looked at in spectral methods in dimensionality reduction. And also, we then calculate the mean, which is based on this gated recurrent units and the weights that emanate from the gated recurrent unit towards the label. So the interesting thing now is that if you look at this and what we've seen now, we can actually combine this, the relations to the dimensionality reduction and create a fully fledged system that does fusion within the framework, and so you do a two-in-one type of modeling. So you detect your emotion, also reduce dimensionality within this model. So, and in terms of training, so it turns out that then maximizing entropy is actually the convexual of maximizing the conditional log likelihood. So we compute the log likelihood with respect to all the weights, the derivative of the weights, and we can use backpropagation throughout the different layers and through time. And of course, the realization, we apply some weight decay and drop out. And then for inference, all we do is then we're looking at the most likely labels, and that is the mean of the distribution. That's what we look for. So just a quick note on the results then. So what I've done is that so this is the first 2 minutes of some arousal video, the audio signal, and you can see that these models they actually do pretty well. They're able to follow the audio signal. They're able to predict it, they're able to predict it very well. And there are some overshoots there between the models. And what I've done is that I've compared the CCRNF to the LSTM, and there wasn't really a significant difference between, so in some different, depending on the modalities, so that's another thing, depending on the modalities, you find that there are some significant differences between the two, but then in general, they're pretty comparable. And this comes to the phrase that in some cases, you look at what modality you're working with and then decide on the model that you want to use. So kind of like using an expert system or ensemble of learners. And you get, for the type of data sets we're working with, because they actually data sets that are in real life, so it's very difficult to recognize emotion. So this is the Pearson's correlations, with 1 being perfect, and 0.7 is, or 0.75 is actually very good for the type of data sets that we're working with. And I also look into, do we actually need to go into deep recurrent neural networks? I mean, is there any benefit into stacking up the layers? And what I found is that if you stack up the layers, so there wasn't really any clear-cut winner, and that's been a story that I've been reading, and a coherent story between the different papers that I've been reading, is that they also can't come out with a clear winner in that, okay, deep recurrent neural networks are the way to go. What happens is that depending on the channel or depending on your modality, in some cases, adding layers helps, and in other cases, it doesn't. So in visual, you can see that as you add more layers, your accuracy dwindles. And for HRV, this is heart rate variability. It also depends on the emotion that you're looking at. So for arousal emotion, it becomes better with the number of layers, but for the valence emotion, just using one hidden layer is sufficient. And I tried quickly analyzing it, so looking at the gate activity, looking at what happens as you increase the layers. And so this is the density of the cells, and looking at what values are contained as the frames, or as the emotion evolves over time. And we couldn't really come up with a way to find, we couldn't find a link between what we see here with our results. So that's still an ongoing research and a very interesting topic in whether we should be going into deep recurrent neural networks when working in emotion recognition. And this is specifically for deep recurrent neural networks. So in conclusion, I've given an overview of the different applications to emotion recognition, and see that recurrent neural networks, or their variants, they do pretty well given the challenges in emotion recognition. And then also we need further research in deep networks and see whether that's a viable option to go into. Okay, any questions? Okay. Okay, so let me see if I can quickly get to the slide. So what happens is that during learning, we actually, I think of the first speaker in the beginning, sorry, I forgot his name. So he gave an overview of how you then train the recurrent neural networks. I mean, so you calculate the error between your estimated, your emotion estimation and your target label. And then you look at what do you need to change, or how much do you need to change the weights in order to be able to, to calculate the total error contributions of the different layers. So what happens then is because of the nonlinearity of the activation function to be used, when you calculate the derivative between the hidden layers, that nonlinearity, so if you're using a sigmoid function, if I'm not wrong, the derivative of that is 0.25. So imagine having 0.25 times 0.25 times 0.25. That quickly becomes a very small number over time, and that's when the gradient becomes small. So with the LSTM, what they do is that they introduce, let me see. So they have here, this part, the forget gate, is basically in charge of that error propagation throughout the different hidden layers. So what they do is that the derivative of ht with respect to ht minus 1 becomes constant, is 1. And that's what we call the constant error flow. So it doesn't attenuate, and that's the introduction that they made. I still have a bit of challenges because there is some attenuation that happens still, so it's not 1, and also depending on your gate and other stuff. But that's their contribution towards this, and that's how it helped. Okay. Okay.
So when you were talking about the continuous conditional recurrent neural field, you were saying you were estimating the conditional probability of an emotion given a sequence of emotions, right?
Yeah.
And I was just wondering, how do you estimate the priors? Like, how do you know what's the probability of someone being disgusted before?
That's the nice thing about the CRF versus the hidden Markov model. We don't actually consider the prior at all. So yeah, so it's just the the prior. Sorry, let me rephrase that a bit.
Because I know that in hidden Markov models that is a big issue.
Yeah.
It's a well-researched field, so yeah.
So I just have to quickly delve into my CRF knowledge here. Let me quickly go here. Let's see. Just that I work on the continuous space, so let me try and remember. So yeah, I think I'll need to go remember it properly, because we don't consider the prior in it at all. So we're just looking at what is the probability of these labels given the input, and so yeah, it's
It's the normal for everyone, right? We can assume the same prior for everything, but in the model,
yeah, just I drew a blank here with regards to the CRF, because I've been mostly on continuous conditional, which then we have a different formulation for it. So I'll maybe read up, or we can talk later and then remember again. Yeah, how to do it.
I'm not an expert.
Yeah.
It kind of looks like you're modeling the joint as a single thing instead of breaking it up as a likelihood times a prior in that equation.
So you were right when you said you're just modeling the prior directly,
Yes.
right? Because this is just a discriminative.
Yeah.
Model. So you were right when you said you're already.
Yeah, or it considers the prior within it. Yeah. Yeah, because you're modeling based, so you're analyzing the whole data and then trying to, so yeah, I probably can't find a proper way of describing it, of explaining it. Yeah. Okay. Oh, sorry. Okay.
Which distance metric did you use for your data, and changing it, what influence does that have on the Laplacian and on the Gaussian?
Can you repeat the first part of the question?
Which distance metric did you use
Oh.
for your data, and how does it influence the Laplacian and the Gaussian?
So depending on the feature, I've been either using Euclidean, and if it's the features that have histograms, then I use the histogram intersection kernels and stuff like that. I've not really done a study of comparative analysis properly to look at the use of different distance measures and how they influence that. What I know, I think what I've concentrated more on is with the kernel. I mean, with the Gaussian, it's very sensitive to the bandwidth, so the sigma, and that's what I've been trying to do to optimize that value based on the distances then. So I've just, I guess, went for histogram interkernels based on histogram features, and then for the other ones, just blindly used Euclidean distances in that case. Yeah. Any, okay.
How does the one baseline voice, is that completely, some people talk more relatively naturally than others. Does that just come
Yes, actually, that's one of the challenges within emotion recognition is the variance within the expressions it differs a lot amongst people and everything. So it's one of the major challenges that come in. So let me try to think quickly. So I don't explicitly go and look into how but it's one of the reasons why we don't actually achieve a very good recognition rate or a near perfect recognition rate, because the intravariance for a person conveying a certain expression over and over is very different over time anyways. Yeah. Okay. I think in the...
Okay, let me just thank you for talking.
Okay, thank you.